So, in this lecture we will continue from where we left off, but before doing this, let me talk a bit about notation. Just like we had notations for point groups, we also have notations for plane groups, and we will be using what is called as the international notation for plane groups. So, let us look at one of the earlier diagrams, come to the notations. This is where we had started deriving the plane group. So, let us look at plane group, the first one where we added basically no symmetry to the oblique lattice, and this is simply would be called as P1. Now, P stands for primitive. So, the oblique lattice is a primitive lattice, and we have added no symmetry to it. So, the letter P followed by 1. This is enough to tell us that it is an oblique lattice and no symmetry has been added. We do not need to mention oblique. It is obvious because there is no other plane group which would have this particular notation. Coming to oblique lattice, added the two-fold symmetry or the point group 2. Well, just like we had called P1, this we will call as P2. This is again primitive, so it is P2. Coming to four-fold, I think it should become quite clear now. The notation would be P4. Hexagonal lattice with a three-fold symmetry added to it, or a point group 3, P3. We added six-fold here, or point group 6, this becomes P6. Now, we have coming to the rectangular lattices, primitive rectangular plus the M point group, that is basically adding the mirror plane. Well, this would simply be called as PM. And then we come to centered rectangular. Well, centered rectangular, here instead of P, I will use the letter C. So, C stands for centered lattice. So, if I look at it, I have the point groups that so far we have plane groups that we have developed P1, P2, P3, P4, P6, PM and CM as well. And so far you can see that we have only developed 7 plane groups. So far what we have done, we have added only the point groups 1, 2, 3, 4, 6 and M to the various lattices. Now, we still are left with a few more point groups. Which are the point groups that we are left with? Well, we are left with, so the remaining point groups so point groups remaining 2 mm, then I have 4 mm, then I have 3 m and 6 mm. So, let us start with the 2 mm point group, and this 2 mm point group will go into which kind of net? It will go into the primitive rectangle. So, primitive rectangular lattice, add to this 2 mm. If I add this, so this is my primitive rectangle, lattice points only at the corners. I add 2 mm, which means that I will have a mirror plane here. I will have a mirror plane like this. So, I want to put that two-fold rotational symmetry at the corner. So, this is how the 2 mm will be added. The translations would take it obviously to all the corners. But we also know that new mirrors will come. One will come in the center vertically, another will come horizontally. This is the combination of a mirror and translation. Combination of two-fold and a translation puts a mirror in the center of the translation. So, therefore, very clearly the two folds will come here and also in the center of the cell. So, essentially what we had started was this. This is my 2 mm and I had added this 2 mm onto the primitive rectangular cell. One thing is very clear in this, that there are no glide planes here, because any attempt at trying to do this, for example, I could consider this mirror and this translation. This is a lattice translation. I could take that, except that the parallel component would also be a lattice translation, which you can inspect and find out for yourself. Now, let us take a centered rectangular and add 2 mm to that. Centered rectangular, adding 2 mm to that. Let us see what happens in this. I have a lattice point in the center as well. Now, adding 2 mm, keeping the two-fold rotational symmetry at the corner, and then just like what we did in the earlier cases, we will take this two-fold and the mirrors everything to the various lattice points. But in this case, I will also have to go to the centered lattice point as well and put a two-fold. Now, let me put some motifs in this. So, if I put a motif here, the mirror will reflect, change the handedness, and this is a mirror as well here. So, this will reflect, change the handedness back to right handed, then again the horizontal mirror reflects, changes the handedness left handed. This left handed object gets reflected as right handed, and we come back to the starting point. Now, all of these motifs will get copied to other lattice locations. And also to the lattice point in the center. Now, what else can we do in this? Well, clearly, just like what we had done in when I put just the mirror in the centered rectangular. So, let us see what will happen to those mirrors. The same thing will happen. We will get lots of glide planes in this case. So, for example, if I take this mirror and translation from the top corner to the center, this will produce a glide plane right here. And obviously, there will be another glide plane that will show up here as well. We can now take a horizontal mirror. Let us say we take this mirror, and again from the top corner I take a centering translation to the middle point to the middle lattice point, that we will have to produce another mirror like this. So, these are all glide planes. Are we done? Well, not yet, because we have not yet looked at the two-fold rotational symmetries. So, if I look at the two-fold rotational symmetries, so let us say I look at this particular two-fold. This two-fold, in fact, followed by the horizontal translation, obviously will produce the two folds here, but we are still not done. Take a two-fold, the same two-fold on the left top, and do a translation to the center lattice point from the left top point. We will obviously put another two-fold in the middle of the translation, and hence one will get two folds. Now, this completes the centered rectangular when we add 2 mm. And continuing with our notation, the primitive rectangular added 2 mm would now be called as, the plane group would be called as P2 mm. Centered rectangular adding 2 mm would be called as C2 mm. Pretty straightforward notation that is used, and again just this notation is enough to take care of everything. The notation itself will tell us that we are in the rectangular crystal system. Now, we have looked at primitive hexagonal net when we added a 3-fold and a 6-fold, but now to that primitive hexagonal net I can add the point group 3m, I can add the point group 6 mm, and let us see what happens when we do this. So, let us start with primitive hexagonal with 3m. Now, let me first draw the cell. And the 3m point group, it should be mirrors going like this through the 3-fold. So, this is my 3m point group. Now, how do I add this 3m point group? In fact, we can add this 3m point group in two different ways to the same cell. So, I will draw this diagram another place. So, I have to show two different, in fact, two different plane groups will get evolved from this. One way of doing this is to add it in such a way, so we orient this 3m point group such that the mirrors are either along the cell edges or they are perpendicular to the cell edges. Let us first look at along the cell edges. If I add it along the cell edges, so my first of all let me add the 3 folds. And then add the mirrors. So, I am saying I am going to first add the mirrors along the cell edges. So, there is a mirror like this, and there is a mirror which will go in this fashion, and of course, the third mirror would be along the diagonal. And then similarly, the translations will take these mirrors to the different cell edges, and at every corner I will have 3 mirrors. So, this is how the mirrors get distributed. Another thing I have not yet added, there are also obviously in the P3 group, the 3 folds would also be here. Now, let me focus on couple of mirrors. Let us say I look at the mirror M1, and I should also say this is my vector A, this is my vector B. So, I am focusing on mirror 1. So, I am focusing on the reflection operation sigma 1, follow it with the lattice translation B. So, my lattice translation is this. Now, what will this do? The lattice translation B is at an oblique angle to the mirror M1, and therefore, it should produce a glide plane. Now, how does it produce a glide plane? So, focus on the translation B. Now, this translation B can be decomposed into 2 components. There will be this component, which is the perpendicular component, no, that is not right. We are looking at mirror M1. So, the mirror M1, I will have 2 components, one along the mirror and then one perpendicular to the mirror. So, to go from let us say point A, the lattice point A to the lattice point B, there is a vector B involved here. We can also go from A to B by first going like this along the mirror, the parallel component, we reach to the midpoint, basically A by 2 we travel, and then we travel perpendicular to the mirror. So, this is my T parallel, and this becomes my T perpendicular. And therefore, where are the glide planes going to be? The glide planes would be, take the perpendicular component, and midway in the perpendicular component, the glide plane would be like this. Similarly, there will be a glide plane in this fashion. And then if you take, let us say, mirror M2, so doing the operation, so sigma 2 followed by, and this time we will take the translation A. Now, I leave this to you to figure out, but this would give me a glide plane out here, and in a similar, through symmetry itself, there would be a glide plane as well here. So, let me just reiterate that this particular mirror, we can call it as sigma 1 tau. So, this is sigma 1 tau. Similarly, this one I will call it as sigma 2 tau, and so this sigma 2 followed by translation A gives me sigma 2 tau, and then the rest of the glide planes will come automatically by the 3-fold rotational symmetries around it. So, this is one kind of plane group. In a second plane group, where we put the mirror planes perpendicular to the cell edges, what would happen there? So, I will not complete the solution here for that, but I will leave it partly for you to think about. So, now I have the 3 folds here, and the mirror planes this time would be, so this is perpendicular to the cell edge and it is at the midpoint of the cell edge. Similarly, there will be a mirror plane in this fashion. Then I will have a mirror plane like this. There would be a, and all of these mirrors that I have drawn are perpendicular to one or the other cell edge. And then there is a mirror plane along the long body diagonal of the cell. As a result, we will also have a threefold out here, and for convenience we always kind of divide this into two equilateral triangles to make this figure clearer. Now, I am going to leave this to you to figure out where are the glide planes located in this. So, you have to work out some mirrors to take. For example, you could consider mirror M1 and you could consider mirror M2 and consider the following combinations. So, reflection operation 1 followed by the vector B. So, my vectors are A here and B here, or take the operation of reflection operation sigma 2 followed by the lattice translation vector A. The solution to this would give you the locations of the various glide planes, but all of these will come out to be glide planes. So, glide planes where are these located? Think about it. I will give the solution in the next lecture, and I will also talk about notation for this. Now, we can't just say P3M because both are two different plane groups that we are evolving. So, we will talk about the notations also in the next lecture. Thank you.